I'm James Barr, and I'm an Android developer at Uber.
I'm Sweers. I am no longer an Android developer at Uber, but I am an Android developer at Slack over in New York. If you want to follow along with our slides, there will be a link in the description below this video.
We've been librarians in large code bases for a number of years at this point, and we wanted to share some of the lessons that we've learned over that time with you. We're hoping that these should be generally applicable regardless of the size of code base that you're working in. First off, let's look at a simple example. So say we have this subscribe method here. We use it for RxJava. The RxJava portion of that is not really relevant. All you need to know about this is just that it accepts a callback that returns you an emission of a value. Now, years ago at Uber, we had a problem with error handling. In RxJava, if an error comes down the pipeline, if you don't have a custom error handler in your subscription, then it will just crash the app. And people didn't seem to really pay attention to that or be not aware of it. So to try to improve this situation, we banned usage of consumer directly and put in something a little bit more descriptive. It was really clever. And so we had this crash on error consumer, which was a base abstract class, but we tried to make it ergonomic to use, so it only had one abstract method. The IDE would automatically implement it for you. It was easy to jump through. And another side goal of this was to have this base class try to trace better stack traces for us whenever an error did happen. Anyone who's worked with RxJava knows that sometimes you can really get lost in the weeds of where an original subscription was that led to some exception you have in your production. So several years later, we had this ubiquitously used everywhere in the code base. Remember, we had banned usage of regular consumers, so this is what the linter said you had to use. We also now had Java 8 Lambda syntax available though, but we couldn't use them because this is just a base class, not a single abstract method in an interface. So that was sort of a bummer. It also turned out that the original goal of having people be more cognizant of how they were using this in error handling wasn't really working out. People were just using this because the linter told them to. And so we weren't accomplishing really some of the original goals that we had set out. We had also figured out a more, we'll say, passive way of collecting better error tracking. So we didn't actually need this. So we went back to the drawing board on this. We looked at it and said, well, long story short, we still get the better error tracking that we want. And it turns out that making people write the word crash in it doesn't actually make them think about adding error handling more often. So let's just ditch it and we can have more readable, simpler code. We also ended up open sourcing that stack trace tracking as a library called RxJava. Now, this is cool, but we still had all of those other usages in the code base, literally thousands of them. And now all of those are tech debt. Really, a lot of debt, like just thousands and thousands of usages. And for a lot of code bases, this is a kind of debt that really just becomes instantly forever debt, or until you delete that code. It's not really something that is ever going to get put on some team's OKR map to migrate away from, because it still works before. It's just less readable. It's never going to be really high priority. For us, though, we migrated them all in a couple of days. No regressions, no formatting issues. Everything went into production, and we had to go off without a hitch. But how, you might be wondering as an anonymous audience member watching this, how exactly does one safely yeet thousands of files of tech debt out of a code base at once? And that's what we'd like to talk to you about today. So a couple of years ago, Jesse Wilson from Square gave a great talk called Writing Code That Lasts Forever. And we're going to talk about some similar things here, but it's more about code that I guess other people write. So it's not just your own code, but rather helping everyone write code that lasts forever.
A great way to help others write better code is to already have many examples of good code in your codebase to learn from. But what exactly is good code? While setting that criteria is ultimately up to you, a minimum bar for quality could include things like code that builds quickly, is well tested, and has documentation. On the other hand, some things that might detract from quality are duplicated code, usage of deprecated APIs, and unmodularized code. It might be difficult for your team to reach an agreement, so I recommend that you start with some less controversial criteria and then refine your definition over time. After you have determined your criteria, you can audit the health of your codebase and collect data for each of the factors. Ideally, you can set up a CI job or periodic task that collects these metrics for you in an automated fashion. This allows you to create graphs and easily track the quality of your codebase over time. In order to quickly summarize the health of your codebase, consider creating your own quality score. This score would be some combination of your code quality metrics, weighted more heavily towards the criteria that you find to be most important. The score also provides a way for you to set overall quality goals for your codebase.
So now that you got your report card from Professor Barr, let's talk a little bit more about this tech debt. So fixing is obviously one thing, but prevention is preferable, and your first line of defense is always going to be API design. You can't misuse what can't be misused. Now, we could talk all day about this, or at least I could talk all day about this, but let's go through some simple principles here. Remember, these aren't rules, they're just sort of guidelines. One of the easiest ways that you can use this is limiting your API surface area. Now, this is multifaceted, but the core principle here is a metaphor that a good hammer isn't a good screwdriver. A few easy examples. So take our hammer class here. Very simple. Do you intend for hammer to be subclassed as something else? No? Cool. Then make it final. In fact, I think you should make it final by default, because at the end of the day, there's an old line from effective Java that inheritance should be designed for. And if you're not actively thinking about how this could be inherited, then don't. If you want to change that later, you can remove final, but it's a lot harder to add final to it later if someone is already using it. Next thing that we can look at is controlling visibility. Now, with visibility, you get a little bit of help from Java where the default is package private. In Kotlin, everything is public by default, which is not my favorite part of the language. In my opinion, you want to go with private by default, and then you can move up through package, internal, protected visibility, etc. as needed. Lastly, you can introduce factories. Now, factories you can think of as often a convenient, semantically meaningful replacement for a constructor. The other side of this, though, is that you actually have a lot more flexibility in your construction, not only having to limit it to the exact class that they've invoked. You can also actually return subclasses. If it's an interface, you can return different interfaces or different implementations of it. And in general, it's just giving you a lot more flexibility down the line. And these things, when sort of put together, in my opinion, really add up over time, maybe after about 2.5 years, give or take. So that's easy enough. Now, another side of API design that I like to talk about is consuming interfaces. So you may have heard about composition versus inheritance. This is a slight sort of tweak to that, where this is more about if you're accepting user code into your library or into your API somehow that someone else is going to be implementing, then I really like the approach of just making those interfaces. You can have some built-in implementations of that are sort of out of the box, batteries included, instances that they can use, but making sure that you are communicating directly with just an interface keeps your code honest, also makes it easier for you to test, and it adds a lot of flexibility for users that want to use it. Next is using Fluent APIs as a form of navigation. Now, Fluent APIs, especially if you worked with a builder, we're all familiar with it. Now, by using it as a form of navigation, what I mean is that, say we have this remove nail function here. Whenever you remove a nail, then you might want to, say, immediately do something with it. Perhaps dispose of it or recycle it or something. Basically, if there's an obvious next step that you want the user to do with it, then you can actually put that directly into the API so that you can immediately bounce them into that step or wherever they need to go on to next. So if we look back at this as a whole, basically when you're writing an API, you want to ask yourself, does this put the user on the right track? While also at the same time, and perhaps a little bit more privately asking yourself, is this going to limit me later when I try to make changes? Two more things in the API space that I want to talk about, but that exist at a more macro level. So the first is API versus implementation. Now, this isn't a new concept. You have the notion of interfaces and implementations of them, etc. But you can actually enforce this at a project level. Let's take a look at our Hammer again. So right now it's under we'll say Hammer project. And we might have other projects that use the hammer and nail APIs. We have a couple of libraries, we have an app. The libraries use it, the app uses it directly. You might have some nice dependency injection structure where a hammer is created and then passed back down to libraries. Now, what happens though is that every time we recompile hammer, these are all going to recompile. So another approach I like for helping solve this is to separate the API and implementation modules. Now, what this means is that after we've restitched our dependencies here, now, whenever we change our implementation, only the app is going to have to recompile. You get a lot of other benefits of this too, with better parallelization of your build, and you also have a slightly cleaner dependency setup. The last API change to improve your project overhead is more of a implementation of this pattern called using, I like to call it an app build config pattern. So quick refresher, build config is something that anyone who's worked in Android is familiar with, where you get this class of static constants generated and available for your app. We can actually use the previous pattern to only generate one of these and also make it more testable. So what I mean by that is if we look at our build config class here, we can actually sort of tease out this API interface from this. And then now we have a interface API, and we can put that into a separate module. And then we can actually just stick the implementation of that in our app and expose the rest of it to consuming libraries downstream. Better yet though, do you even really need this implementation in your app? I mean, how often is this changing? How often does that need to affect all of the code being compiled also in your app? Usually, I think probably not the case. So you can even take this, stick it in an implementation module, and make your app depend on that. You can put all your variants and configuration in there, try to reduce the amount of configuration and overhead for the Android Gradle plugin. And then speaking of that Android Gradle plugin, it's very easy to then go through, run through your application variants, and disable build config generation and save yourself that overhead. If you want some more resources on this, there's an API design as an art talk that I gave a few years ago. Here's also Jesse's Writing Code That Lasts Forever talk. Effective Java obviously is a great resource. If you don't know what Effective Java is, it's basically sort of like the Bible of writing Java code. And I have an example pull request of an implementation of this app build config pattern if you're interested. Now, you can't solve everything with API though. Code review is obviously important too, and not all safety can be baked into design. Now, there's not much that we want to cover here, but there's two very simple things that I want to highlight. It's mostly focused around communicating ideas and using code review as an opportunity for education. Code review itself doesn't scale well for repetitive things, so you should try to keep them focused on solutions. The first that I want to cover is teach, don't tell. So rather than just saying, don't do this or just use this, instead try to be more proactive in your explanation and include a lot more detail. So saying things like use X instead of Y for reason Z, things like that. I know it sounds like a very minor detail, but it's something that really accumulates over time, especially if you're working with or mentoring more junior engineers on your team. The second thing is approving with nits. And this is more of like a pattern that I like to encourage, but the basic principle here is that nits are comments that are optional, and you're actually explicitly describing them that way by having the word nit at the front of it. These are extra information or things that are maybe tangentially relevant for the author that you want to share, and you should use them generously. One thing that's really important with this pattern, though, is that you have clarified expectations within your team for how you want to handle these in review. The pattern that I really like is that, as I mentioned, nits are optional. If something is approved, then that means that it's mergeable as is. Any comments that are left with an approval that are not clarified to be nits are expected to be addressed before merging, but I'm trusting my colleague to actually go through and do that before they hit merge. And that's really it on code review. It's a really refined tool, I think is the best way I can describe it. It's the most refined tool in your belt for sure. And it's what's always going to get you the best result. But it's also the most expensive and time-consuming one to use. And as such, you want to make sure that you're not wasting your time with it bike shedding, which leads us to static analysis. because you can't bike shed with a linter. So static analysis is, in my opinion, essential, especially if your team and codebase grow beyond really a trivial size. Sometimes it's preemptive, and sometimes it's retroactive. And we'll see some examples of this. There's two main types that I'll mention here, but we don't really have time to dig into the nitty-gritty of, and that's lint in Android and error-prone for general Java code bases. I highly recommend learning how to not only introduce them into your code base. Lint usually comes for free in an Android project. Error-prone has a very simple setup with a popular Gradle plugin, and you're going to want to not just bring them into your code base, but also explore learning how to write custom checks for yourself for your own code base, your own patterns, and whatever else you find valuable to try to analyze within your team.
Now that we've created our new API and linted against additional usages of the old API, it's time for us to refactor our code to reduce our tech debt. Let's take a look at some of the available tools that we have. To start off with, simpler refactors can just be done with find and replace. This can be used in IntelliJ or even any other text editor. Most editors offer directory filtering and regex support for more complex replacements. On larger projects, you'll get better performance working in the terminal. Using tools like find, xargs, and sed will help you work faster when modifying thousands of files and avoid freezing your IDE. When working in Kotlin code, there is a useful feature for deprecations. The @deprecated annotation signals that an older API should no longer be used. But Kotlin's version also allows you to provide a hint to the IDE. The hint is used to signal to the IDE that a replacement is available. The developer can then choose to make the replacement locally or even throughout the entire project. Android lint is another way to suggest code replacements to developers. This is a nice choice since it analyzes Java, Kotlin, and XML resources. These suggested fixes show up in the IDE, giving engineers fast feedback and quick resolution without even needing to perform a build. Structural find and replace is just like the regular version, but with added code intelligence. It's especially useful when trying to migrate code that can't easily be distinguished with just a regex. To try it out, navigate to Edit, Find, Structurally Replace. IntelliJ has a wide variety of templates to start off with. This particular example was based on the method call template. Instead of just entering plain text or regex, variables are used to represent parts of the AST, that is, fields, methods calls, parameters, etc. You can configure the properties of the variables, like type or count, in order to refine your search. Structural replace helped us safely perform the crash on error consumer to Lambda migration mentioned at the beginning of this talk. On a side note, right now this is only supported in Java, but you can follow along in this ticket for updates on Kotlin support. Another option for migrating code is creating your own custom IntelliJ plugin. Don't you sometimes wish that there was a built-in option in IntelliJ to remove Hungarian notation? With a plugin, you can just add your own refactor tools, leveraging the power of IntelliJ. A plugin would let you invoke IntelliJ's built-in refactoring tools, such as structural find and replace, programmatically. This makes it very useful when you have to do multiple renamings or other operations. We used a similar custom plugin that invokes structural find and replace for migrating the AssertJ test APIs over to Google Truths. You can see a similar script at the link below. And if you need even more customization, an option you might not have even thought of is to use a scripting language like Python or even Kotlin to transform your source files. This is especially good for transforming source files based on the output from another tool, such as reports from test failures or lint. We used this method to perform our Android X upgrade using the CSV files of the package and module mappings provided by Google, since the migration tool was only available for Gradle. This was a very large change in our Android monorepo, but we made it as safe as possible.
Next, let's talk about de-risking change. So automation gives you a lot of confidence, especially whenever it's machine-generated patches or fixes in your code base. But unfortunately, computers can't do everything for us yet. Not every change is big. Some are small but significant. If you've ever updated Play services, you have probably learned that you can often measure the rollout of their Play services by your crashes dashboard. You don't have to necessarily wait until rollout to try to vet some change, though. So the first example of this that I want to talk about is using shadow jobs. So what's a shadow job? A shadow job is a silent, master-only job that applies and incubates a new change. That change can be as small as a dependency update or a build tool update. Sometimes it can be a large swath of updates or an automated script of a migration. Whatever really floats your boat, it's just there to run in the background, not on PRs, not blocking anyone from merging, and give you a sort of over time testing and incubation of a new thing before you release it to everyone or into production. It can also act as a sort of crystal ball into the future for different tools that you use, etc., allowing you to update to those whenever they release stable versions with confidence, knowing that you've really vetted this well in advance. Some examples of this include at Uber, we use a shadow job to basically incubate new Kotlin version updates before merging them directly into master. At Slack, we actually have a number of things that we check in shadow jobs, anywhere from a matrix including AGP 4 and 4.1 betas. We have Android X alphas. We have different versions of Java as we look to try to update which JDK version we compile with. You can really sort of go to wherever your heart's content is on this, but it's a really, really easy, powerful thing to do, especially if you're using a very simple CI setup like GitHub Actions. It's very easy to make a matrix that just runs master silently and does this on whatever cadence you want. Next, let's talk about offensive programming. Now, we all know what defensive programming is, and offensive programming is just the opposite. So in defensive programming, you just assume the worst and you try to gracefully handle anything that can come your way. With offensive programming, you maybe still assume the worst, but you're also going to basically just fail quickly and explosively. And the idea here is that you should be trying to do offensive programming in your actual debug builds. You can take the same problems and try to fail silently and log in production if it's a recoverable situation, but for your debug builds, at the end of the day, it's much better that you catch it now rather than it manifests itself in a release down the line and you have to push a new update to fix it. Let's do a quick example of this. So Uber generates code from for their network models based on API specs. Now, in the beginning, when we worked on this, we used raw collections, so list, set, map, etc. But you'll notice that this is Java code, which means that these collections are all mutable inherently. And that was a problem because these models were supposed to be immutable, and it turned out that people would get these collections back and then start adding their own things to it. So the obvious fix for this is to make them immutable. Seems easy enough, but they'll just fail at runtime. And it's extremely unsafe to kick this directly into production because we have no real notion of safety whenever we do this. We might have unit tests that cover this down the line, but we don't really have a good guarantee of that. So what can we do? Well, we can keep it as a list, but under the hood, we make it behave like an immutable list in this generated code, just in debug builds. After a few weeks of ironing these issues out as they would come up in local debug builds, then we could safely promote it to release, and I don't think we had any issues. I'm just going to say that we didn't. I'm pretty sure we didn't. Oh well. Not everything can be smoothed over like this, though. And next, James will talk about unflaggable changes.
When you cannot feature flag the changes that you are making, you should take some additional steps to improve the safety of the changes. One thing you can do is build a copy of the app from a branch for stakeholders so that they can test the changes before they are merged. Another thing to consider is whether you should do the refactor in multiple commits or a single commit. Multiple commits make it easier to revert just a part of the change if something goes wrong. You may also have to use multiple commits in order to get it through your CI pipeline. If you have a monorepo, then you might not have any other choice than doing it all at once. When it comes time to actually merge the changes, be sure to do so after a scheduled build cut or over a holiday freeze to maximize the amount of soak time the change has before it's included in a production build. You also don't want to thrash in other engineers that are trying to merge their features before the deadline. After the large changes are merged, let others know. Send an email to your engineering group, being sure to include the task details, the commit, a short link to docs, and rebase steps, scripted if possible. Since comms often get lost in large companies, send a Slack message to your engineering room with the same information. And share the news at your weekly team meeting. And even send a carrier pigeon or a raven to that person that never checks their messages.
So to wrap this up, basically there's a lot of different tools and techniques that you can use. We've covered measuring your debt to start out. We've covered API design, code review, static analysis, refactoring and migrations, and ultimately de-risking changes if all else fails. And we hope that you can take these tools back to your code base and apply them. Like we said, it's not rules, they're just guidelines. And a lot of these are the kinds of things that they're not useful for everything, but whenever you run into a situation where they help, they can make a world of difference.
We hope that these lessons will help you keep your code base clean. Thanks.